The generic data model was developed in the Productive 4.0 project as a relational database model. In the SC3 project, we want to transfer the manufacturing domain knowledge that the model contains into the digital reference. The first step was transforming the entity relationship model into an ontology model compatible with digital reference. The ontology is further improved by mapping different databases' data to answer decision-making challenges, create transparency across the various databases, and reuse data in other applications. This demonstrator will show how the ontology is developed and improved, map and feed the data from different sources, create rules and check for coherence, answer expert competency questions to validate the ontology, and show a use case with real data for real-time dispatch. In Reutlingen semiconductor fab, data is stored in different databases due to inheritance and how the fab evolved. Every time a new solution is developed, a new mapping is created between the solution and various databases. That is a massive effort that requires many experts from different fields. The ontology can minimize the mapping effort to just one mapping into the GDM ontology. Other applications, particularly simulation, RTD, and AI, can access understandable data. One feedback from the data architect was that we should model the ontology into an object-oriented programming environment due to its flexible usage in other applications. In other words, we can create an ontology object-oriented programming model mapped to the scenario's datasets, existing databases, and then ship to other applications. One can define the classes and provide labeling and documentation. Create relationships as object properties between different classes and define cardinality. Data properties can be easily assigned to each class. Taking advantage of having the ontology objects, we can map the data from various databases into ontology. Establish the instances and the relationship between the objects. We are ready to start working with the instances using the SWRL rules or SPRQL query. This way, we can answer different competency questions and help the decision-making in real-time dispatch. Based on several internal interviews with domain experts from Bosch, we verify the ontology with different competency questions. We can check which equipment is available for production or at any other state by either using the SWRL rules and a reasoner or by querying the data with Sparkle. We can filter which equipments are busy or under maintenance. The advantage of SWRL rules is that it can create new instances based on conditions. An important information in real-time dispatch is what is the next lot to be placed on the machine. Therefore, we can first query the dedications for each of the lots, at which chamber it can be produced, and to which equipment the chamber belongs to and how man chamber the equipment has, the more the better. We can filter the data based on the lot number or the equipment number. One rule in RTD is dispatch sort according to a specified order as they arrive at machines. This is the simplest dispatching rule, and also the one that seems fairest when dealing with customers, is first in, first out. The FIFO rule simply processes jobs in the order in which they arrive at a machine. What are the priority levels for each lot, and where the next production step can be processed? Each lot with dedication has a priority based on the FIFO principle, processing time, customer due date or any other parameter. To better understand the situation, we can investigate the graph that is generated. All the lots are represented in red and the equipment in green. We can see that some lots can be produced with several types of equipment and some with just one or none. Based on this, we can identify bottlenecks and overcome them by deciding where to send the lot best to the less used equipment. In supporting the decision, we have the option to dispatch all the lots based on several rules that can dispatch all the waiting lots to the next machine or storage. Depending on circumstances, we have the option of sending the lots manually. For example, we can select one lot to be sent to a specific equipment based on the priority or the shortest processing time to process the small jobs first. Once dispatched, the reasoner changed the state of the equipment to busy and the current state of the lot to loading. Once we dispatch the lots to the available equipment, we can check where to transport the waiting lots that cannot be processed next. We can check every lot's current state, its information, location, and how long it has been in this state. Looking at the graph, we see that many of them are sent for loading into the equipment load port, which is represented in green, and others are waiting in the storage, located in the middle of the graph. Based on the RTD capabilities of the ontology like introduced routes, operations, recipes, processing time, start time, end time and step, several KPIs can be calculated like chamber utilization and approximate the lot throughput. Supply chain level can take advantage of such information for planning and delivery.